All right, hello everyone. So this is a recording for a missed Phys 231 lecture on Friday, October 24th. Um, so what I want to do today is I want to start talking about diodes and rectifier circuits. So a rectifier circuit can be thought of as converting an oscillating AC signal into a constant DC signal. Um, so diodes are semiconductor devices. So what I want to do first is I just want to talk about a simple fluid analogy for a diode. This lecture will focus on what diodes do and how they can be used to perform useful functions for us, like an AC to DC conversion. Later in the class, we will start talking about how semiconductors are made and how those semiconductors can be used, manipulated to make devices like the diode and ultimately a transistor. Okay, so we'll start with just a general description of a diode. So the diode is a semiconductor device that acts as a one-way valve. That is, what it does is it passes current in one direction, but not the other. Okay, so let's think about a simple fluid analogy. Um, I want to think about first of all, let's just think of a pipe. So here's some kind of hollow pipe, and what we're going to do is we're going to try to pass a current of fluid through this pipe. So the pipe has some walls with some thickness. So if I want to flow fluid through this pipe, what I have to do is I have to provide a pressure difference to drive that flow of fluid. So if I say that over here, we're at pressure P1, and I want to flow the fluid from left to right, I have to make the pressure on the left, P2, bigger than P1. So in this sense, it pressure differences drive the flow of fluid or the mass flow. That's analogous to like voltage differences driving the flow of charge or an electric current. So to flow fluid through a pipe, we need to establish a pressure difference across our pipe. So delta P is used to drive a flow of fluid, just like a voltage difference drives the flow of charge. Okay, so that's not a doubt. That's kind of like a resistor. The pipe has some resistance to the flow of fluid. The smaller the diameter of the pipe, the higher its resistance. So to make a diode, we're going to have to add something to our pipe. And so here's our diode analog. So we'll start by just having the regular opening of the pipe. And so we'll extend this way, like so. Okay, and so the new feature is we're going to have like a little gate inside of our pipe. So let's imagine we have some wall thickness. And then at some point, we're just going to step that up. And then we'll continue along this way. And we'll have a step over on this side as well. And then I'm gonna have like a little hinge here and a flap. And so here's our flap, like so. And usually gravity will just keep that flap closed. And so I'm gonna have my P2 on this side. Here's P1. I'm gonna call the flap a gate. So our gate is held closed by gravity. If you want, you could think of maybe the hinge is spring-loaded, so it also kind of holds that gate shut. All right, so if P2 is greater than P1, we get fluid flow from left to right if the pressure difference is sufficient to push our gate open. Okay, so remember, pressure times area is like a force, and so with a big enough pressure difference, we apply sufficient force to the gate that applies a torque that's going to allow the flap to swing open. If on the other hand, we made P1 bigger than P2, then that force is just going to push the gate closed harder and harder and harder. And so there will be no fluid flow. The fluid tries to flow right to left, but gets blocked by the gate. And so what we've designed here is like a one-way valve. And you can literally go to the hardware store right now and go find one-way valves that operate more or less just like this. Okay, so let's go back to that first case where we say P2 is greater than P1, but we're going to make that pressure difference really small. So if P2 is greater than P1, but by just a tiny amount, then we don't apply sufficient pressure, or let's say sufficient torque to open the gate. And there is no fluid flow. So in our one-way valve design, what we need to do in order to allow the flow of fluid is to provide a pressure difference, P2 minus P1, that exceeds some threshold that's required to get this gate open. So we have to overcome an energy barrier to open the gate and initiate the flow of fluid. All right, so if I wanted to make a plot, I could make a plot of something like pressure difference. We'll say delta P is P2 minus P1. That's my x-axis. And then on my vertical axis, we'll put the fluid flow rate, which is just the fluid current. And so we talked about this fact that we have to overcome this little barrier. And so I'm going to call this our threshold. So it's the minimum delta P required to open our gate. Okay, so we know that anytime we are at a pressure difference that's less than this threshold, the fluid current is going to be zero. But then as soon as the gate opens, we have a rush of fluid from left to right. And so we get this kind of upward tick in the fluid current, and the current is going to be determined by other components that are downstream. So if we have some long thin pipe that has a lot of resistance, there'll be a low current rate through our valve. If we have big fat pipes downstream, then the flow of current will be high through our gate. Okay, so there's electrical versions of these one-way valves, and those are called diodes. So in electronics, diodes act as a one-way valve. And as I said, once we've talked about semiconductor materials and how we can dope them to manipulate their electrical properties, we'll be able to assemble a diode from two pieces of semiconductor materials that are joined together at a junction. And we'll see how this energy barrier comes about and how we have to overcome a certain threshold in voltage to initiate this flow of charge. So it's a one-way valve for electric current or charge flow. So let me show you the circuit symbol for a diode. It looks like this. It's this little triangle with a vertical line at one end. So I'm going to call this side side A, this side is side B. And I'm going to label this as the negative end. We'll call it N. And this is going to be the positive end. And we'll call that P. So this is our circuit symbol for a diode. The way that you can remember which direction this triangle points is that it's like an arrow and it points in the direction that current can flow. So we can make current flow from left to right in this diode. And so it follows the direction that this arrow is pointing, if you like. Okay, so on the other hand, if we try to flow current from A to B, from right to left, that is always going to be zero unless you have some special diode that breaks down above a certain voltage. But we're not going to consider that case here. So if VA is greater than VB, so we have a higher voltage on the A side than the B side, then I is equal to zero. If VB minus VA is greater than some threshold voltage, then I is not equal to zero, and we have current flow. And that current flow will be from B to A. Okay, for a diode, this threshold voltage is typically 0.6 or 0.7 volts. So we have to exceed that threshold for VB minus VA if we want to get current to flow. So we require voltage of the positive side, I'm going to call that the P side, to be greater than the voltage on the N side by at least 0.6 to 0.7 volts, which is our threshold voltage. The exact value of the threshold voltage will depend on the type of semiconductor used and the details of the fabrication of the device. So we have to exceed 0.6 to 0.7 volts for a non-zero current. For our diode, we can make a similar plot that we did for the one-way valve for the water pipe. This time I'm going to plot the current on the vertical axis, and I'm going to plot a delta V is VB minus VA on the horizontal axis, and then we'll label our threshold voltage. Threshold voltage right there. And anytime we're less than that threshold voltage, the current will be 0, and then the current jumps up after we exceed that threshold voltage. And again, the exact value of the current that we're going to get will depend on other components in the circuits, like resistors and batteries and so on that are downstream. Okay, so let's think about how the diode actually behaves when incorporated into a circuit. So we're going to start by considering a so-called reverse biased diode. Reverse biased diode means that this delta V is VB minus VA is going to be less than V threshold. So either it's delta V is a positive voltage that's less than, say, 0.7 volts, or maybe it's a negative voltage. So we're going to call those reversed bias, and in this case, we get no current, as the plot above shows. This plot above here is typically called like an IV characteristic. Okay, so let's make a simple circuit. It's going to have is a battery, plus minus, and this time I'm going to specify that this delta V supplied by the battery is less than V threshold. Okay, and then we'll incorporate our diode right here. And I'm going to put a resistor and then close the circuit. And what we'll do is we'll take as the output of our circuit as the voltage across the resistor. I'll call the resistor RL. Here's our diode, here's our P side, and here's our N side. Okay, so in principle, we would have a current flowing clockwise around our circuit, but we've already said, because we haven't exceeded the threshold voltage to turn on the diode, we're going to get 0 current. And so in this case, we could replace this with an equivalent circuit in which the diode presents essentially an open circuit. It's like it's not even there. If we break the circuit, then there can be no current, which is exactly what the diode is causing. So this is our delta V. It's still less than V threshold. We'll just say I is equal to 0. This is our RL. If we're measuring the output of our circuit across this resistor RL, well, the voltage across a resistor is just I times RL, but I is equal to 0, so we get 0 output. Okay, so a reverse biased diode is equivalent to an open circuit. Okay, So let's consider the other case. What happens if we make our battery have a voltage greater than this threshold voltage? So we're going to call that the forward biased case. So forward biased diode. So the diode is on and our current is not equal to 0, is what we're going to expect. Okay, but really the layout of the circuit is the same. We have our battery followed by our diode, and then we have our resistor. We're calling it RL. And we're going to measure our output as the voltage across this resistor, V out. Call this terminal A and B. So this is the P side, and this is the N side. I guess we could go and label over here. This is B and this is A. Okay, so now here's delta V is greater than V threshold. And so this time we will have a current and it will not be 0. Okay, good. So let's see, what do we get for the output? So we know that a forward biased diode requires VB minus VA to be equal to V threshold. This is the voltage required to turn on the diode or to make it conduct. Okay, so in this case, the forward bias diode acts like a small battery. So if we focus just on the diode, we would have something like, here's our diode, here's terminal B and terminal A, and then what we need to do is we need to consume some of the voltage in order to turn the diode on. And so what we have is the B side, which is the positive side of the diode, we've been calling it. That is where the positive terminal of the battery goes. And then on the N side, when the diode is conducting, passing current, that's where the negative terminal of our battery goes. And so our equivalent circuit becomes, so equivalent circuit. All right, so we'll have our initial battery. This is delta V is greater than V threshold. And then our diode gets replaced with a small battery. And this is going to be V threshold. And then we have our RL. We close the circuit and we measure the output. It's just going to be whatever the current is times RL. Okay, and so let's go back and look at this IV characteristic. And we kind of had this funny feature where the current apparently can take on any value it needs after we exceed V threshold. And so we'll see in this first example how the rest of the circuit determines what that current is going to be. All right, so what we're imagining here is that we now have a current in this circuit, I, and so our first job is to try to determine what that current is. And so we'll just do a standard loop analysis, a Kirchhoff loop law. Oh, come on, analysis. Let's go. Analysis. Okay. So we'll start here in the bottom left corner. The first thing we do is we cross our battery, so we get delta V. Then we cross our V threshold, but we're going from positive to negative terminals. So we're going to go minus V threshold. And then we cross our resistor in the direction of the current. So we get minus IRL. And then we're back to our starting point, and so we get 0. So if we solve for IRL, which is equal to V out, that's just equal to delta V, the battery voltage, minus the voltage required to turn on our diode V threshold. Okay, good. So that's the one-way valve action of the diode. In one case, it allows no current. In the other case, it allows current to flow, but there's a little cost. We have to consume V threshold to overcome this barrier that's needed to open the gate of the diode. All right, so let's consider how can we use this to make a useful circuit. And so what we'll talk about is a so-called rectifier circuit. I like to think of this as a AC to DC converter. All of the outlets in the walls that that are in all our homes and buildings, they output a oscillating sine wave for the voltage. It's 120 volts RMS at 60 hertz. But a lot of the devices we use, like our laptops, cell phones, tablets, whatever, they all run off of batteries, and we have to charge those batteries. Those batteries are charged with a DC constant voltage. And so we need a way of taking the AC voltage that's supplied and converting that to a constant DC voltage that powers all our that's needed to charge all of our portable devices. Okay, so I want to consider something very similar to the circuits that we just analyzed. All I'm going to do is I'm going to replace the batteries with function generators that output sine waves. Otherwise, the circuit is the same initially anyways. Here's our RL, here's our diode. We're going to take as the output as the voltage across RL. And there's some current in our circuit, at least sometimes. And here's our V in. So this is our AC input, like so. So if V in is less than V threshold, which will happen a lot of the time, more than half the time, right? The sinusoidal input, the sine wave is half the time a negative voltage. And so that is not going to forward bias our diode. And so during this entire time, when the input is negative, and in fact, when it's small and positive, when it's positive but less than V threshold, the current will be equal to 0, and our V out will be equal to 0. This is what we've been calling the reverse bias case. If on the other hand, V in is greater than V threshold, then the current is not equal to 0. And we've already worked out that the output will be the input minus V threshold, about 0.6 or 0.7 volts. And this is what we've been calling the forward biased case. All right, so we can draw some plots here. I'm going to draw my Vn as a function of time, and it's just going to be a sine wave of some amplitude. So let's see if we can draw a reasonable sine wave. Okay, that's not too bad, I guess. And so this sine wave goes between some positive V naught and some negative V naught. Okay, maybe I can extend this. Okay, so below, what I'm going to do is I'm going to draw the output of our circuit. That is the voltage across RL. And so that output I'll draw as a function of time as well. There's T. Okay, this is going to be V out. So what's going to be important are the times when the input voltage exceeds our threshold voltage. And so I'm going to draw the threshold voltage in green. Something like this. Maybe I'll make it a dashed line. All right, good. So this is V threshold. And so some important times are going to be when the input crosses the threshold voltage. And so I'm going to drop down some lines here. Like so. All right. Okay, let's start with the easy part first. We know that whenever our input is less than the threshold voltage, our output is going to be 0. So we're going to get 0 here, we're going to get 0 here, and we're going to get 0 here. Okay, when we are forward biased, the output is equal to V in minus the threshold voltage. And so it should have the same shape as the input. It'll just be lower in amplitude by an amount of V threshold. And so our output would look something like this. And this value here, the peak sits at V in minus V threshold. So the peak of V in is V naught. So this peaks at V naught minus V threshold. Okay, good. So we were trying to make an AC to DC converter, and we certainly haven't done that yet. If we look at our output, it's clearly not a constant DC voltage. But what we have done is we've managed to make an output that doesn't average to 0. If I average the input, it's half the time positive, half the time negative. So over many cycles of that period of oscillations, that's going to average to 0. Whereas my output is either 0 or positive. And so if I average that over a long time, it's going to be some non-zero positive average. So while we haven't made a AC to DC converter yet, we have made something that starts from an average to 0 and then ends up with a non-zero average. So we've made some progress because while V in averages to 0, V out averages to something that's not 0. It averages to some positive value. Okay, but we want to make some improvements. We want to make something that has an output that at least approximates a constant DC value. So here's what we're going to do. To improve our AC to DC converter, we're going to put a capacitor in parallel with RL. Okay, so I'll draw that circuit. So here's our input VN. There's our diode. We're going to have our RL. We'll close our circuit. So this was what we had originally. We had this V out measured across RL. So now the addition is we're going to add a component. We're going to add this capacitor C in parallel with RL. So just to get an idea of what's going to happen, notice that R and C are in parallel. So that means they're always going to have the same voltage. So while the diode is conducting, we're going to get a current through this RL. That's going to make some non-zero voltage across the output. The capacitor is going to charge to whatever voltage it needs to match what the voltage across RL is. But then when the diode's not conducting, we get an open circuit where the diode is. And what will happen is our charged capacitor will discharge through this resistor RL. But we're going to arrange it so that that discharge is very slow. So when the diode is reversed bias, instead of the output suddenly dropping to zero, what we're going to do is we're going to allow the voltage across the capacitor to bleed off through the resistor very slowly. Okay, so let's see how this works. So we'll start with the forward bias case. So the forward biased case doesn't change really. We still find V out is equal to Vn minus this threshold voltage. So let's draw the circuit. The equivalent circuit is we have to replace the forward bias diode by a battery. And we have to get the orientation right, the positive terminals on the left and the negative terminals on the right. So now we have our resistor, RL. We close our circuit. Here's Vn. I'll put in my capacitor, C. That's the new component. And then this is our output. V out is still equal to Vn minus V threshold. What is new now, however, is that when we have some positive output voltage, our capacitor must have positive charge on the top plate and negative charge on the bottom plate. So our capacitor C charges to V out while the diode is forward biased. And so that means I is not zero. Okay. So let's do the reverse bias case. So for a reverse bias diode, that acts like an open circuit. So we'll draw an open circuit in place of the diode. And then we'll have our RL in parallel with our capacitor. But now remember, if our diode was just forward biased, that means our capacitor is charged. So it's still storing that positive and negative charge on its plates. And so now we get our V out here. So what will happen is this capacitor will discharge through the resistor RL. The VN is not really, it's not part of the circuit anymore because we have an open circuit. And so really the only important part of our circuit is the parallel capacitor and RL and the discharging of this capacitor through RL. So as we bleed off charge from the capacitor, V out will drop, but we're going to try to make that discharge very slow so that we get an approximately constant V out. Um, Eventually, what will happen is because our input is periodic, it will eventually go positive again and pass that threshold voltage. And in that case, the diode goes forward biased again. We get some current through that diode, and whatever charge we have bled off that capacitor will be replenished by the next positive cycle of our input. Okay, anyways, back to the reverse bias case. So now the capacitor C discharges through RL with a time constant, tau equals RLC. Okay, and so we're gonna select RL and C such that tau is much greater than t, which is the period of the sinusoidal input. So this ensures that during the reverse biased part of the cycle, the capacitor discharges only a small amount. Okay, so let's try to draw the input and output again for this revised circuit where we've added the capacitor in parallel with R. So here's T, here's Vn. I'll try to draw a few more cycles this time. So this is going to be our V naught, and I'm going to make the threshold voltage. I'll make it look a little bit smaller here. So this is going to be our threshold voltage, something like this. The threshold. All right. And so now underneath this, we will draw our output. So this is going to be V out. We know V out's always going to be positive, so I'll put my horizontal axis down here. Like so. Okay, and then what we have to do is we have to drop down these vertical lines at when the input crosses the threshold. So it's going to be something like this. Yeah, approximately like that. Okay, make these dotted. Okay, so this time, what I'm going to do is I'm going to start with the output voltage. What did I use? I used blue before. Yep. So let's start at the peak. The peak of this is going to be, we know it's going to sit at V naught minus V threshold. Okay, so now what will happen is initially this is going to kind of follow the input. But let's imagine we've gone to this peak and now the input starts dropping off. As the input drops off, the current decreases, um, and eventually the diode goes reverse biased. But the output voltage doesn't drop to zero. It doesn't drop to zero because the capacitor is charged up and we don't instantly lose all the charge on the capacitor. It has a discharge through the resistor. And what we're going to do is we're going to make that discharge slow. So there's our slow discharge. And then what happens is the diode goes forward bias again because now we're back in the positive cycle of the input. And this will cause the capacitor to charge back up. So whatever charge bled off initially will be replenished. And then the discharge starts again. And then we're back to another positive part of the cycle where this climbs back up and then the discharge starts again. And so this procedure just repeats over and over and over again. So I've drawn it here so that we can kind of see this discharge of the capacitor. But if I make the RC time constant very long, then what we can do is we can really suppress this so-called ripple. They call this change in voltage is like the ripple. And the longer I make my RC time constant, the smaller that ripple gets. Okay, so with the capacitor in place, the average of V out increases and looks more like a constant DC voltage. Okay, and so this circuit is called a rectifier circuit. In fact, maybe we could be more specific. Notice that we've only really made use of the positive part of the input cycle. We've more or less thrown away the negative part of Vin. The diode is reverse biased during that part, and all we're doing essentially is waiting for the positive part of the cycle to return. So for that reason, the rectifier circuit that we have just looked at is called the half-wave rectifier because we're only using the positive part of the cycle. So let me just draw the circuit again. It's a function generator, diode, and then a resistor in parallel with a capacitor. And so this circuit is called a half-wave rectifier. So RL, C, V in, V out. This is the half-wave rectifier. Oh, that's not right. Half-wave rectifier. So in lab number 6, I think it's going to be, you're going to build this rectifier circuit. And in fact, we're not going to talk about it here, but in lab 6, you will also, after building and studying the half-wave rectifier, you're going to build a variation, the so-called full-wave rectifier, which uses both the negative and positive parts of the input cycle. And the effect is that the amount of time that the capacitor discharges is going to be reduced substantially because we don't have to wait for the positive part of the cycle to come back. We will be charging our capacitor both with the positive and negative parts of the cycle. And so that means our ripple factor will decrease because the discharging time will reduce significantly. So in lab number 6, you will build and study the half wave rectifier first before moving on to implement a full wave rectifier that uses both the positive and negative parts of the VN oscillation. All right, so I think that's where I'll stop for this recorded lecture. So thank you very much, and we will see you in the in-person class shortly. All right, thank you very much.